Welcome to MRS Bulletin's Materials News Podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Sophia Chen. Think about the last time you dropped a coffee cup, or maybe even thrown one.
If you throw it, it just fails catastrophically, right? It just fractures.
That's Rohit Pratush Behera, a mechanical engineer at Nanyang Technological University in Singapore. He's talking about the characteristics of typical ceramics. They're mechanically strong, which means they can withstand a lot of force, like if you stack objects on top of it. But they're not tough, because once they start to break, that initial crack spreads extremely easily throughout the entire object. Hence, the ceramic mug shatters. But Behera's research team has developed an unusual type of ceramic. Their material is strong and tough in that it has a lot of resistance to crack propagation. You can stack objects on it and it won't easily shatter.
It won't fail catastrophically, rather than it will absorb some energy and then fail after some time.
To make this material, they actually drew inspiration from biology. In particular, they borrowed microscopic designs found in 3 different creatures: a mollusk, a mantis shrimp, and a human. In the case of the mollusk, they mimicked the inner iridescent material of some seashells, known as nacre, or mother of pearl. They replicated the microstructure of the nacre, as mechanical engineer Hortense Leferron explains.
They are assembled in a brick and mortar structure that looks very much like a brick and mortar in a wall. The key difference is we don't really have a mortar in our case. We have an interface.
The bricks in naturally occurring nacre are made of calcium carbonate, but instead of calcium carbonate, they used aluminum oxide particles for the bricks. Microscopically, you can visualize this as little round discs, 6 to 8 microns in diameter, in horizontal layers, one on top of the other. Instead of having some sort of mortar, there is instead a weak interface with no microscopically visible material between the 2 layers of brick. If you imagined hitting the material and cracking the disc nearest to the surface, that crack would propagate through the interface and stop there.
It's very difficult for the crack to flow through your material completely. Because of this, it doesn't fail catastrophically.
They stack the bricks into a helical structure. This spiral shape is inspired by the microstructure of the dactyl club of a mantis shrimp. This is a crustacean found in shallow tropical ocean habitats. The dactyl club is an appendage that the mantis shrimp whips around to break the shells of crabs and other prey.
The mantis shrimp is an animal that has an arm that looks like a hammer that can actually break the seashells.
To create this helical structure, they use an external magnetic field to align the discs on top of each other. The aluminum oxide in the discs are designed to respond to the magnetic field.
And you vary the magnetic field as you are pouring your slurry onto your mold. This can create multiple orientations.
By adjusting the magnetic field, they can change the alignment of the discs.
We can play with the orientation layer by layer.
The third and final biological inspiration for the material is the human tooth. A tooth has a hard enamel casing around it. Like a tooth, they encase the aluminum oxide helical structure in an extra protective layer made of alumina nanoparticles.
What happens in teeth is, on the top you have one protective layer, and in the bottom you have one energy dissipating layer.
To make the material, they first make a slurry consisting of a suspension of particles and water. Then they shape it using slip casting, and then they apply the magnetic field to create the helical microstructure. Then they center it in an inert atmosphere using an ultra-fast, ultra-high temperature process that just takes 1 to 2 minutes. They tested the material with standard bending tests and by purposefully putting cracks in the material and monitoring the way that it cracked. The unique aspect of the work is the design process. Tweaking the properties of the material is simple.
We are just playing with the orientation, composition, and then we are able to get different properties from it.
Potential applications of the material could be for dental implants or protective wear, such as helmets. However, they point out that their samples were about 1 to 2 centimeters in length and about 5 millimeters thick. They will need to create larger samples for them to be useful in applications, and the size was limited in part by the strength of the magnet they used. In addition to making the samples bigger, in future work, the group is exploring different compositions for the slurry. They're also looking into incorporating a mortar between the discs. They also want to combine the process with extrusion-based 3D printing. This work was published in a recent issue of Cell Reports Physical Science. My name is Sophia Chen from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org and follow us on X at MRS Bulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.